So here's an example. Yeah, open it. Of a paraboloid, or my favorite paraboloid, z equal to 9 minus x squared minus y squared, over the region between between -2 and 2 and y equals -2 and 2. So I could also actually let me do one more thing here. I just thought of, that's a good idea. Always the same color. So there's like the shadow of that surface in the XY plane. And so you can see what we're doing is we're limiting that surface, right? If you do away with this for a second, that's the entire surface, the parabola 9 minus x squared minus y squared. But then we are limiting the domain of x and y to being between x being in the square, right? The square that goes from -2 to 2 for x and y. And so on that surface, then you can kind of see, well, if we zoom in a little bit, no, that's too much. Can I not, do I have to be centered all the time? I guess so. Oh, well. So if you zoom in, you can see some points here. So we can see there's an absolute maximum right there at the top. There's 4 absolute minima that all have z values of 1. 2, 2, 1, 2, 2, negative 2, 1, negative 2, 2, 1, and -2, -2, 1. And then there's also these other points that we had to check. These other points, they're on what I like to call the walls. So that point right there, that point is on the wall x equal to 2. So we set x equal to 2. We then found the derivative of the remaining piece, which gave us 2y equal to 0. We got y equal to 0. So the critical point along that wall where you kind of have a maximum on that x equals 2 is a y value of 0 and a z value of 5. But it's not the absolute maximum. But it could have been. That's why we had to check it. In a similar way, let's pull up another one. So I'll move this over here. We also have a plane. Yeah, open it. Why do you think I'm clicking on it? Because I want to. Yeah. So here's a plane, z equals 4 plus 1/2 x plus y. And so a plane, like if you think about the plane being the roof of your house and it's kind of tilted, one corner is going to be the lowest point on the surface and one corner is going to be the highest point. Well, I should, yeah. And I really do like this, having the shadow down here. I think it's smart. So there's the shadow of that. So right, this point here over that corner is the lowest point, and this point over here is the highest point. Here, if you look at this function, z equal to 1/2 x plus y, any partial derivative is going to equal a constant. The partial with respect to x is going to be 1/2. The partial with respect to y is going to be 1. So you're not going to get any critical values. Meaning the only places we have to check are where? Where you always have to check the corners. You always have to check the corner. Just like in 17a, when we checked for absolute maxima on an interval, you always had to check the left endpoint and the right endpoint, and any critical points in between. So here we're checking all the end points, and there are no critical points in between. And then thirdly, let me grab this again. I do not want to do the nice thing that I want you to do. There we go. If we look at this hyperboloid of one sheet, this one actually does have its absolute extrema on the walls, which I think is kind of cool. Gosh, yeah, okay. So this surface, right, is sitting over still the same square, x between -2 and 2, y between -2 and 2. But now we have, right, an absolute maximum, 2 of them actually, that point right there, when x is 2, y is 0, and z is 7, and that point right there, when x is -2, y is 0, and z is 7. And then we have absolute minima on the other wall over at 0. I can't click on that point because it's too hard to see, I guess. Here, I can click on it there. At 0, -2, -1, and 0, 2, -1. So it's kind of nice to see that when you have these surfaces over a limited domain, you can get absolute extrema anywhere. By anywhere, I mean at any corner or along a wall or in the middle of the surface or of the region, I should say. Those are all the places you can get an absolute max or an absolute min. kind of nice to see it, I think, as opposed to just kind of have someone try to draw a not great picture. Okay, hopefully I've given my computer enough time to maybe let me do anything. Cool, finally. Oh my goodness. All right. So let me make this big over here. So what I would say as far as finding, maybe, as far as finding absolute extreme or any kind of extreme, whether it's relative or absolute, typically the hardest part, I think, is actually finding the, oops, what am I doing? Oh my God. Is actually using my computer, apparently. Can I move you? Please. Yes, thank you. Okay. Will you hide away now? Thank you. All right, cool. Little suspect there. Why? Oh my gosh, it's just a day for things not working as well as I'd like them to. Okay, there we go. Finally, what I wanted. Okay, so what I would say is the the hardest part, I don't know, the hardest part, I think, is typically finding the critical points. Evaluating them once you know what you're supposed to do is not too hard, whether it's trying to find relative or absolute, but finding the critical points can be really challenging. So let's look at a couple examples and then we will talk about LaGrange. So, last day of January. Let me see. Let me grab these examples that they know I like. Yeah, you're fine. Okay. So let's say we've got this example. And we'll do one relative and then we'll do one on a closed interval. So let's say we have f of xy equal to the function 6x squared plus 6y squared minus 3x squared y minus y cubed. Yeah, we should do that other one too. There's another one I really like. It's good. I'll find it in a minute here. And we want to find and classify the relative extreme. So all the time, the first thing we do is find the partial derivative, set them equal to 0. You could also say you're setting the gradient equal to the 0 vector. It's the same thing. So fx is going to be 12x minus 6xy. Fy is going to be 12y minus 3x squared minus 3y squared. That looks funky. Set these each equal to 0. Again, I will point out, I think it's worth seeing, this here really is the gradient of f as a vector. This here is the 0 vector, which is just 0, 0. You don't need to know that, but it's kind of cool to say it. So, which of these looks like it's easier to deal with? The first equation or the second equation? I would agree. I think the first equation is easier. I don't have any squares in the first equation. It looks simpler. So let's try dealing with the first equation. So I set 12x minus 6xy equal to 0. I can factor out a 6x. I'm left with an x. Sorry, not an x. I'm left with a 2 minus y. So what solutions are there to this equation? Well, either x equals what? Or y equals 2. I cannot stress heavily enough. 0, 2 is not a critical point. Because if you plug in 0 for x and 2 for y, sure, this first equation will be 0. If you plug in 0 for x and 2 for y, 12 times 2 minus 0 minus 3 times 4 is not 0. It's 12. So when you find two values here, you're just saying these are solutions to this equation being equal to 0. And then you have to plug either one of those into the other equation to find the corresponding value that makes the other equation 0. And it can be a little bit tricky sometimes to realize that. So looking at x equal to 0, I'm going to say 12y minus 3 times 0 squared minus 3 times y squared has to equal 0. So I'm going to find the y value that goes with x equal to 0. So I've got 12y minus 3y squared equal to 0. I'm going to factor out a 3y. I'm left with 4 minus y. So either when x is 0, I either get y equal to 0 or y equal to 4. This is actually going to give me 2 critical points. My critical points from this are going to be 0, 0 when x is 0 and y is 0, or 0, 4 when x is 0 and y is 4. And you can check if you want to, if you plug in the point. Well, I think it's obvious if we plug in the 0, 0, both equations are going to equal 0. If we plug in the 0 for x and 4 for y, I think it's obvious the first one's 0 because you get 0 minus 0. To see the second one 0, you actually have to do it, right? 12 times 4 is 48, minus 3 times 0, minus 3 times 4 squared, 3 times 16 is 48. So you have 48 minus 0 minus 48, which is 0. So we can see, oh yeah, 0, 4 is a critical point because both partial derivatives are equal to 0 when you plug in that pair of x and y. And then finally, we should also check out what's happening when y is equal to 2. So we got that from the first equation, so we're going to plug it back into the other equation. So I plug in y equal to 2, I get 12 times 2 minus 3 times x squared minus 3 times 2 squared equal to 0. So I have 24 minus 3x squared minus 12 equal to 0. So I have 24 minus 12 is 12. 12 minus 3x squared equals 0. And I divide by 3, I guess. So you have 4 minus x squared equals 0. And then this factors as 2 minus x times 2 plus x equal to 0. So you get x equal to 2 and x equal to negative 2. So I have 2 more critical points. I have x is 2, y is 2. And I have x is 2, x is negative 2, and y is 2. Oh, 4 critical points. Let's see what they are. So to do that, we got to find d. And to find d, I would start by looking at my partial derivatives there. So to find d, which is fxx times fyy minus fxy squared. Be careful, I saw someone miss the square recently here and got the wrong value because of it. D is going to equal, so fxx is going to be 12 minus 6y. Fyy is going to be 12 minus 0 minus 6y. That's convenient. And fxy is going to be 0 minus 6x squared. And if I check the other way, fyx is also negative 6x. So it's good to, I like to confirm that the mixed partial derivative, either way I do it, does end up being the same. That's usually a good check to make sure you've done things the right way. Because they should all be for the problems we're doing. So that's my capital D. Now I'm going to plug in each critical point to this and see what I get. So let's figure out what I'm going to have d of 0, 0. And here's what I want to point out. You kind of want to not simplify this. Like I really don't want to multiply this out. I guess you could write it as something squared, but I think it's really, really nice to know that whatever I get right here is my value of fxx. Whatever I get right here is my value of fyy. So when I plug in 0, I get 12 minus 0 times 12 minus 0 minus 0 squared. I don't care that it's 144. I just care that it is positive. So if it's positive, what does that mean? Or, what does it mean? It's not for sure. It's not a saddle. But if it's positive, it means it could be a max or a min. To figure out which it is, you have to look at the second derivatives here. Both second derivatives are positive. So since fxx is positive, that means we're concave up, which means we have a minimum. So 0, 0 is a relative minimum. Let's keep going. Let's plug in. What was my other points? 0, 4. So d of 0, 4. Again, I'm plugging in 0, or sorry, I'm plugging in 4 for y now. So now I get 12 minus 6 times 4, which is negative 12, times negative 12, minus still 0 squared, which is still going to be positive. It's actually still going to be 144. So I still get the same result in that it's still, since d is positive, is going to be a max or a min. But now, because my fxx or my fyy was negative, that means we're concave down. And if we're concave down, that means we had to have a maximum. Oops, I pointed at the wrong thing. So 0,4 is a relative max. And I believe these last 2 points end up being saddle points, but let's obviously find out. So I'm going to do D of 2, 2. It was 2, 2, right? Yeah. So that's going to be, so if I plug in 2 for X and 2 for Y, 12 minus 12 is 0. 12 minus 12 is 0. And -6 times 2 is -12 squared. So is this whole thing positive or negative? Definitely negative, which means we have a saddle. And I'll point out the same thing is true when you plug in to -2, 2. So D of -2, 2, same result. You still get 0 times 0 over here. You do get minus positive 12 squared when I plug in a -2 for X and I get -6 and -2. That's still going to be negative. So I still have a saddle. So I have both at 2, 2 and -2, 2 saddle points. The saddles at 2, 2 and -2, 2. I do think it's nice to see what this looks like. So let's take a real quick look at Desmos here, which I hopefully left up smartly, but you know, oh, I did. Cool. Let's give ourselves a new graph. Sure. What's the easiest way to do that? I don't know. Yeah, go ahead. So let's see. We were graphing. Where'd you go, James? Sorry, it's right here. Z equal to 6x squared plus 6y squared minus 3x squared y minus y cubed. And so I can't see it. I see a minimum. That's all I see. Red's not my favorite color for this. Let's change the color. I like blue. Sure. That's just a personal preference. And I also like to make it translucent. Cool. We zoom out a bit, zoom in a bit, zoom out a bit. Which way am I zooming here? Oh, why does that look super funky? Did I do something weird? Let me make sure I've got this right. 6x squared plus 6y squared minus 3x squared y minus y cubed. Why does that look so incredibly awful? Usually this does not look so bad. I'm really kind of confused as to why it looks. I guess, yeah, but now I'm too, yeah. Let me try. Oh, okay, we can kind of see it here. So if you look, oh, you know what I should do? I should just plot the points. So obviously we can plot the point 0, 0, 0. And then we also can plot the point. Let's see, we had 0, 4, these. Let's you know what we should do? I'm going to make this graph a little bit different. I'm going to multiply the whole thing by like 1/10. So that, oh, that's not good, James. Come on. So that I can make it not as high. Does that work? Maybe. Yeah, that's a little bit better. That's, yeah. So, sorry, I feel like this is not, there we go. Okay. So you can see your minimum there. You can see your maximum there. And then the saddle points are not as easy to see. I feel like this one usually looks better. I don't know what I did to make it look so off. Wow, okay. Ooh. Well, there are saddle points there. Yeah, 0, 4, comma. Not my best today. Where are those? Sorry, I'm like, where are the saddle points? They should be like, let's read. There we go. Yeah, they're there. Okay. Right there. There's a saddle point where it's kind of a maximum this way and a minimum this way. It's not super easy to see, and I'm sorry about that. I feel like it's usually a little easier to see. Yeah. Yeah. Yeah, yeah, that's okay. All right. Gosh, time. There's never enough time. So should we do another one where we talk about? Yeah, we need to do one more. Sorry. I want to move on to the other new thing, but we should really talk about one more example because I feel like one more thing I want you to see. So let's look at, where'd you go here? Sorry. Fine, I'll just make something up. So let's say we want to find the absolute maxima and minima of f of x comma y equal to 3x squared plus 2y squared minus 9x plus 8y. Oh, sorry. Yeah, that's about par for today, I think. All right. It's still going fine. Perfectly fine. On the triangle whose vertices are, let me do a real quick check here, that'll be fine. Are, sure, let's go big. Give me 1 sec. That's gonna be terrible. I'm gonna make one. No, I'm not. That's gonna be fine. The vertices are -1, -1. And then we have 4, 0, 4, -1, and -1, 4. So we want to find the absolute maximum and minimum of this function on the triangle I've just described, which we should draw. So here's the triangle I'm talking about. So I've got the point -1, -1, and then 4, -1, and then -1, 4. And not surprisingly, it's a right triangle. Okay. So the process is always the same, it's just kind of tedious. So first, we're going to find critical points. So take my partial derivatives, fx is 6x minus 9, so that equal to 0. Fy is 4y plus 8, so that equal to 0. We end up getting 6x equal to 9, or x equal to 9, 6, which is 3/2. And we get 4y plus 8 equals 0, so 4y equals -8, so y equals -2. So our point is 3/2 comma -2, and it's not in our domain. Right? The point 3/2 comma -2 is like right there. That was not by design. I made up the question and then I made up the region. Sometimes your critical points are not going to be in your domain though. So we're not going to worry about that. We still have to look to see if we have any and if they live in our domain. So the second thing we're going to do is find any critical points on any of the 3 walls or the edges. So the edges / walls. And I should cross this one out because we're not going to use it. Again, it's not in the region, right? We're looking for points that are in here. So now we have 3 walls. We have the wall x equals -1 over here. We have the wall y equals -1 down here. And this wall here, it's the line between the point -1, 4 and 4, -1. The equation of that line is pretty easy, actually. It's got a slope of -1 because you go over 5 and down 5. And it's got a y-intercept of +4. So without too much effort, I think it's reasonable to say that the equation of this line is y equal to -x plus, sorry, a y-intercept of 3, not 4. if you check, right, if you plug in 4 for X, you get -1 for Y. If you plug in -1 for X, you get 4 for Y. So that definitely works. And people often give examples like this where the triangle has a slope of -1 or +1, so it's not too hard to find the equation of the side that's slanty. So looking at the walls, let's start with X equal to 1. Sorry, X equal to -1. So I'm just going to plug in -1 to my function. So I'm going to say that f of -1 comma y is equal to 3 times -1 squared plus 2y squared minus 9 times -1 plus 8y. And then I'm going to take the partial derivative of that with respect to y. So fy at -1 comma y is going to be 4y plus 8. Set that equal to 0. I'm still going to get -2. Which means I don't get a critical point there. Because again, it's out of bounds. I mean, I do have a critical point, it's not in the domain. So -1, -2, no good. I will point out that this is semi-atypical. Most of the time when you find critical points, the problem has been well thought out enough that they end up being in the domain. Let's look at the other edges. So we look at y equal to -1. We do the same thing. We plug in -1 for y. We say f of x comma -1 is going to be 3x squared plus 2 times -1 squared minus 9x plus 8 times -1. And then we take the partial derivative with respect to x, and we get 6x minus 9 equal to 0. So we end up getting x equal to positive 3/2. But now we do get a critical point because y being -1 and x being 3/2 is on or in the domain. So there's our first point that we're going to look at. That was 3/2 comma -1. And then the one that's going to be messy, we're going to plug in y equals -x plus 3 into our function. And I might not have enough room here, but we'll try and see if we can make it fit. So f of x comma, instead of y, we're going to say -x plus 3 is 3x squared plus 2 times -x plus 3 squared minus 9x plus 8 times -x plus 3. And then we take the partial derivative of that. So fx is going to be 6x. I'm just going to use the chain rule here. Bring down the 2, you get 4 times -x plus 3 times -1 because of the chain rule. Derivative of 9x is 9. Derivative of 8 times -x plus 3 is just going to be -8. So simplifying this a bit, fx is equal to 6x plus 4x. And then we have -4 times 3 is -12, minus 9 minus 8 is minus 29. I think we might get something in the domain here. It's going to be really, really gross, though. I mean, really, really gross is debatable. So that equal to 0, you're going to get 10x equal to 29, or x equal to 29 over 10. Oh, but what's the y value going to be? Let's see. If x is 29 over 10 and y is -x plus 3, y is going to be -29 over 10 plus 3, which is 30 over 10. So y is going to be 1 over 10. So I think we're barely in there. X is just a little bit less than 3, and y is just slightly positive. It's like we're right here at the point 29 over 10, comma 1 over 10. Okay, we found all the points on the walls. We found the points that were as a critical point, but it's no good because it's not in there. And this other one that would have been on the wall, but it's not. And then finally, we have to check the corners as well. So here's all the critical points we have to check, which might get a little bit messy. So all the points we have to check are going to be the points 29 over 10, comma 1 over 10, 3/2, comma -1, and then all the corners. -1, -1, -1, 4, and 4, -1. So we plug all of those into the original function, and we see what happens. We don't see what happens. We see which one is the biggest and which one is the smallest, right? We don't see what happens. We look to see for where the biggest is. So f of xy is 3x squared plus 2y squared minus 9x plus 8y. Yeesh. Let's do the nice ones first. F of 4 comma negative 1 is going to be 3 times 4 squared plus 2 times negative 1 squared minus 9 times 4 plus 8 times negative 1. And that's going to end up being 50 minus 44, which is 6. F of negative 1, 4. This is not the important part of this process. It's just the tedious part. I mean, it's important that you can do it, but like, this is not we know how to plug things in and calculate values. We just have to do it to see what we get here. So plugging a negative 1, 4, I get 3 plus 16 times 2 minus 9 times negative 1 plus 8 times 4. So we have 64 plus 12, which is 76. Nextly, plugging in negative 1, we get 3 plus 2 plus 9 minus 8, which is 6. And now for the gross ones, plugging in 3 halves comma negative 1, I'm going to get 3 times 9 fourths plus 2 times negative 1 squared is 1. Minus 9 times 3 halves is minus 27 over 2. Plus 8 times negative 1 is minus 8. Yeah. So I get 27 over 4. 2 minus 8 is minus 6. Minus 27 over 2, which I should really multiply by 2 over 2 to get 54 over 4. So 27 minus 54 is negative 27 over 4. And 6 is 24 over 4. So I get negative 51 over 4, which is close to negative 13. It's actually negative 12.75. Actually. Finally, the one I was been dreading here, 29 tenths comma 1/10. What I might do is I might plug in 3 and 0 and see what happens. Yeah, I might. But just to kind of see if it's close. I plug in 3 and 0, I get 3 times 9 plus 2 times 0 minus 9 times 3 plus 8 times 0, which is going to be 27 plus 0 minus 27. It's pretty close to 0. So I picked a point that was close to the point I'm looking at and got 0. It's definitely, so if I pick a point, right, if I pick a point a little less than 3, that's going to get a little smaller. That's going to get a little bigger. That's going to get a little less negative. That's going to be a little bit, I think 0 is a pretty good estimate here. And 0 is definitely not the biggest thing by a long shot. And it's not the smallest thing by a long shot. So I think it's a safe bet, although you might check on your own if you have a moment, that f of 29 tenths comma 1/10 or 2.9 comma 0.1. This would be a great time to have used a linearization to approximate. We're not going to do that, but like it seems like that this is the kind of thing you would actually use a linearization for. Like, I don't know what that is, so I'm going to do a linearization and then plug that in and see what happens. I'm pretty sure it's pretty close to 0. All right. So much time left for LaGrange multipliers. Sorry. A little sorry. I mean, I'm not sorry to show you things. I'm just sorry that my time management was not more excellent today. Let's talk about LaGrange multipliers. Take a sip. So the idea behind Lagrange multipliers, do we have enough time? So it's another way of optimization, but we haven't really talked about optimization in the context of like these. Sure, we've been maximizing and minimizing things, but usually when you're talking about optimization, you're given like some function of some variables and asked to maximize or minimize it based on some constraint. I'm going to show you a classic example because it is a classic example. So here's the classic example. And I'll kind of make it quick here. We want to mail a box through the USPS that holds as much volume as possible. But we're restricted because the USPS says your box has to have its length plus its girth to be less than or equal to 108 inches. So the requirement is that the length plus the girth is less than or equal to 108 inches. So here's what this looks like in a picture. My box kind of looks like this. Then here's the length. And the girth is the measure around the part that's not the length. So the girth is this measurement here. So if we label the size, excuse me, of this box to say like X, Y, and Z, because that's what I would choose to label it, then the length plus the girth is really, well, the length is Z, and the girth is Y plus X plus Y plus X, or 2Y plus 2X. And we want that to be, well, we want it to be less than or equal to 108, but we want to make the box as volumetric as possible. So we're going to say it's equal to 108. So we use as much of the constraint as possible. There are two ways to approach this. One way is to not do any of the LaGrange stuff. One way is to say, oh, look, I can solve for Z here and say that, is that what I want to do? Sorry. Yeah. Oh, I know. Sorry. Let me back up 1 second. So that's our constraint. We are constrained by the fact that these dimensions have to add to that. That's our constraint. What are we trying to maximize? I want to maximize the volume. And for this particular drawing, the volume is X times Y times Z. There's a couple ways of approaching this. One way, without using the LaGrange multipliers, which I'm not going to do right now because we don't have enough time. But one way is to say, oh, take this constraint equation and solve for one of your variables. Take your constraint and say, I'm going to say that Z equals 108 minus 2X minus 2Y. And then plug that into the thing you want to maximize. So then the volume that I want to maximize is X times Y times 108 minus 2X minus 2Y. Oh, look. Volume as a function of two variables is 108xy minus 2x squared y minus 2xy squared. And we know, or we've had some practice as to how to maximize or minimize a function of two variables. You take the partial derivatives, you set them equal to 0, you find the critical points, and then you test to see if it's a maximum or minimum, and it should be a maximum. But we're not going to do it that way so that I can show you an example of using the LaGrange multipliers. So instead of finding the critical points and then using D equal fxx fyy times minus fxy squared to classify, we're going to do the following instead. We're going to use LaGrange multipliers. So here's how LaGrange multipliers work. And again, on Friday, we'll come back to this example. We'll do it the other way so you can see if they do produce the same results. So use LaGrange. So the thing you want to maximize, we typically call little f. So we're going to maximize little f of x, y, z equal to x times y times z, the volume. And our constraint, we typically call little g. So our constraint is x, sorry, I lost it, z plus 2x plus 2y equal to 108. And I imagine when your teacher talked about this, he brought everything over to one side and had 0 on the other side. He might not have, but it's often what people do, or they make sure you have a constant on the other side. Sound familiar at all? No, constant like 108. He might have said z plus 2x plus 2y minus 108 equals 0 and called this g of x comma y comma z. So let me continue on and then we'll circle back. So what we're going to do is we're going to say that capital F of x comma y comma z comma lambda is equal to little f minus lambda times little g. Does that look familiar? Or do you talk about gradients? Talk about gradients? Cool. So let me show you both ways. So lots of people do is they say, now you take all the partials, you set them equal to 0. All the partials of capital F. So capital Fx is really little fx minus lambda times little gx equal to 0. Partial sec to y is little fy minus lambda gy equal to 0. Capital Fz is little fz minus lambda gz equal to 0. Or, as I'm guessing he might have said it, you have fx equal to lambda gx, fy equal to lambda gy, fz equal to lambda gz, or as he probably actually said it, the gradient of f equals lambda times the gradient of g. Do any of those look familiar? Okay. People often teach it this way because students have a hard time seeing that, but they're equivalent. Okay, so the setup, once you know it, is not too hard. The setup is take all these partials and set them equal to lambda times the other partials. So let's do this relatively quickly here. He tries to say it. So, oh, notice I didn't mention capital F lambda. Because capital F lambda equal to 0, well, the derivative of this with respect to lambda is just negative g. It's just setting your constraint equal to 0, which we already have that written on the piece of paper. I can write it down for you if you want, but it's really not necessary. So capital F or little fx is going to be yz minus lambda times gx is going to be 2 equal to 0. I think I like it better this way. I think I like fx equal to lambda times gx. And then for the next one, fy, so fy is going to be x times 1 times z equal to lambda times gy, which is also lambda times 2. And finally, fz, which would be, oh, sorry, I'm looking at little fz is 1, is not 1. Little fz is x times y. And gz is just 1. So these are my relationships. So fy would be xz minus 2 lambda. Fz would be xy minus lambda. And then I will point out, oh, you know what it's not too bad. What I didn't do was actually write out what capital F was, which I suppose would have been a good thing to do. Capital F of x comma y comma z comma lambda is actually the function x, y, z minus lambda times my g. I don't think you need to do this, but some people like to do it. But I think knowing this is probably the nicest way to do this. Because whenever I do this, the first thing I do is then rewrite it like this. Here's where people do different things. Some people like to divide these equations by each other. That's totally fine. I'm more of the style of taking any two of them and solving for lambda. So if I take these two and I solve for lambda, I have lambda equal to yz over 2, and also lambda equal to xz over 2. If I then set those lambdas equal to each other, this gives me xz over 2 equal to yz over 2, which means x has to equal z. X has to equal y. I can multiply both sides by 2, divide both sides by z. Assuming z is not 0, which it probably isn't. Similarly, I can take any other two equations, so not the same two, but take a different pair. Let's say I take this pair now and solve for lambda again. So now I get xz over 2 equals lambda. Be careful that your z's and your 2's look distinct. And here I get xy equal to lambda. So then I have xz over 2 equal to xy. Divide the x's and you get z over 2 equal to y. Or I'm going to solve for z here. And the reason I'm going to solve for z is because y is the thing that's showing up twice because of what I happen to pick. So I want everything in terms of y because there's y in both of them. So I want z equal to 2 times y. And then what I'm going to do is I'm going to take those things and plug them back into the constraint. So then replacing x with y and z with 2y, look what happens. I get z is 2y plus 2x, sorry, plus 2y plus 2y, and let's say equals 108. And now I'm able to solve for y. So 6y equals 108, so y equals 108 divided by 6, which is 18. 18? I think so. 108 divided by 2 is 54. 54 divided, no. Yeah, it's 18. 18. And then x equals y, so x equals 18. And then z equals 2y, so z equals 36. And that's the process. So big picture here, the process is find all the f partials, all the things you want to maximize partials, and set them equal to lambda times the things you want to minimize partials. I like to solve for lambda, set them equal to each other, and then get relationships between x and y, or x and z, or y and z. So then you can plug those back into the constraint and have the constraint be an equation with just one variable that we can solve. Then you get y, and you go back and find x and z. Last thing I want to say here is that I will point out some people do this differently. I could have totally divided this equation by that equation. What's 2 lambda divided by 2 lambda? What's yz divided by xz? Or what cancels? Right, you get the z's cancel, you get y over x, and if y over x equals 1, then y equals x. Oh, y equals x. You get to the same place, it's just a different way of doing it. It's not the way I have ever preferred to do it, but it totally works nicely. So if you like doing it that way, or a teacher likes you doing it that way, do it that way. I'm happy to do it that way in the future if that's what he says he wants, or if that's the way he's showing you how to do it. It works just as nicely. All right, we'll try to do some more LaGrange on Friday.